Welcome. Good morning, everyone. I'm glad to see you all here, especially after the club night and on the last day morning. So I hope you like the topic we'll cover. My name is Sepideh. Satu is also here, also the chair of the session. I'll just have 2 slides for you to really give you insights into the motivation for why we decided to put together the symposium. Let me see if I can. All right, so we will be covering spatial organizations of connectivity over time scale. And all of the speakers today, their work is really characterized inherently by combining different kinds of imaging modalities and electrophysiological modalities. Okay, I'm still figuring this out. All right. So when we think about the relationship between connectivity, as most of us know it from MRI-driven modalities, especially fMRI, to electrophysiological connectivity, it isn't simply a simple linear relationship where the both signal will represent some kind of a simple sum of the metabolic demands of all the electrophysiological underlying processes. In fact, the electrophysiological signal is so rich that we can define connectivity in a variety of ways. So whereas in the hemodynamic response to the left, we think about connectivity between distributed regions as some kind of a measure of temporal dependency, such as correlations. In electrophysiological signals, we can actually talk about the relationship between the amplitudes of oscillatory rhythms of the brain, or the phase relationship, phase coupling of those rhythms, or even more complicated, various ways of cross-frequency coupling. So here is one example, which is phase amplitude coupling, where the phases of the slower frequencies have an impact on the power of some higher frequency. And Satu Palva is actually going to give us even a more complex view that there are different kinds of cross-frequency coupling modes in the brain. To make matters more complicated, all of these various mechanisms of connectivity actually occur at various different frequencies. So we have parallel channels of communication that can independently be present in the brain, and so that makes the picture really complicated. And I just wanted to really emphasize that we're talking of at least 4 orders of magnitude of timescales here, from the infraflow that we typically measure in both fluctuations to the various bands of canonical oscillations. Just a single data slide that I have. The goal of this slide is really walking you through, I guess, the evolution of my personal motivation in this field. So I've been doing concurrent EEG fMRI for quite some time, but I really didn't, for a long time, think it was possible to derive reliable whole brain connectomes from EEG signals. But thanks to work of a lot of labs, we have come to realize that although the volume conductance problem and the inverse problem is really hard to crack, we are already at a point where we can derive very meaningful connectomes from MEG and EEG. So what you're seeing here is essentially the spatial correlation. So this R value here, R.37, is a spatial correlation between a whole brain connectome of phase coupling derived from source localized surface EEG in the beta band as a function of fMRI correlation strength. So every dot in this scatter plot is one connection of the whole brain connectivity matrix. This is averaged across subjects. And so you're seeing that the connections that have particularly strong connectivity in fMRI seem to be the same connections that have particularly strong phase coupling in EEG. And that's not just true for the beta band, it holds true for all canonical bands. So I'm just plotting this here because most of us rely on fMRI connectivity and we think that's something that's useful enough, and therefore this moderate correlation really should motivate us to start looking at EEG and MEG. And then probably more striking, and this was the turning point for me personally, is that the correlation of phase synchrony in EEG to underlying DTI structural connectivity is not any smaller than that of fMRI to structural connectivity, at least for the parcellation used in this particular study. So all of this data is for concurrent EEG fMRI and then combined with structural connectivity. The structural connectivity is here on the x-axis, and I should note that this is a weighted measure of path length, so therefore the correlation is negative. But what I want to point out is that the fMRI correlation for this data set is 0.4, and for the beta band is 0.5. All right, so to really get the message home here, electrophysiological connectomes are linked to fMRI and DTI-derived connectomes, static connectomes, in all frequency bands. This is true not only for phase coupling, but also for amplitude coupling, which was shown in a different study. So now my last point here is actually from electrocorticography data. So if you still don't trust source localization, this is intracranial data. And what we're showing here is for every different frequency band, here at the bottom, we're showing the spatial correlation of the phase-derived connectivity for 10 individual subjects. So for each individual dot here is individual subjects, and the line is the mean value for those. In brown, you see the correlation between resting state and task static connectomes, and in this blue purplish color, you see split half rest to rest connectivity. So the relationship between rest and task of the core of the connectivity structure is no less than rest to itself. This is something we've known for fMRI for about 5 years now, but it even holds true in intracranial electrophysiology. So a lot of the things are looking similar. So these topics will be covered in depth both in electrocorticography by Aaron Kuchi and in MEG by Satu Palva. But cognition is inherently flexible. And with electrophysiological data, we have the luxury to actually measure those flexible changes in real time. So what's the relationship between dynamic changes in connectivity as we measure them in electrophysiological signals? What's the relationship to time-varying dynamics that has been so popular in the fMRI field recently? And part of what Diego Vidor will say and Jonathan Biazich will show to you is going to cover this topic. So I just wanted to point out that Mark Woolrich unfortunately couldn't join us because of a last-minute health issue, but we thank Diego Vidor, his long-term collaborator, to cover his talk for us. And again, we invited these speakers because of their multimodal approach to this question. Without further ado, Aaron.